Okay, good afternoon, everyone. So today we're going to continue our discussion about the support vector. It's going to be called the support vector classifier. And let's just review a little bit about what we learned last time. So we had this pretty important picture here that tells us several things. So here is the decision boundary between the red and the blue classes. And we know that for any linear classifier, this boundary is also linear in the sense that it's a line or a plane or a hyperplane in higher dimensions. So the first thing we saw that's interesting is that this W, this weight vector, is going to be orthogonal to that hyperplane. And we did a short proof of that. Another thing we saw is that we can see exactly what the intercepts along these feature coordinate axes are from the weights and the intercept term. Another thing we did was we noticed from there that if you scale the weights and the intercept b by the same number alpha, that will not change the location of the boundary, right? So in that sense, you get an equivalent classifier. And the final thing we did is we said it's possible to measure the distance from any point xi to the boundary. And we derive this expression for it. So this is what we call the signed distance, because this is a distance that could be positive or negative. And for one class of samples, when they're on the correct side of the boundary, the distance will be positive. And then for the other samples on the other side, their distance will be negative. So this distance, the sign will depend on the class. Okay, so that's a few things we learned. And then we went on to talk about linear separability. As an intuitive idea, it's pretty simple. So when a data set is linearly separable, you can find some boundary that perfectly separates the data into the two classes. Now, the boundary is basically determined by the B and W pair. So we can also say this a little bit more precisely. Say that the data is linearly separable if there exists some B and W and some positive epsilon, such that for all the scores Zi corresponding to targets 1, the scores are positive, and then for all the scores corresponding to targets -1, the scores are negative. Okay, so that's another way of describing linear separability. So on one side, you have positive scores is one class, and negative scores the other direction, the other class. So that's sort of an intuitive way to describe that. And then we set about trying to simplify this. And the first thing we said is, okay, if the data is ±1, then we can actually merge these two inequalities together into a single inequality. That simplifies it a bit. But then there's still this epsilon. Can we somehow avoid using epsilon? And the answer is yes, because if you divide both sides of this by epsilon, you get B over epsilon and W over epsilon greater or equal to 1. And now this is like equivalently using a new weight and intercept scaled by epsilon. And what we said earlier is that whenever you have this scaling for any positive scalar, you essentially get an equivalent classifier. So from another perspective, if you can find a B and a W that works for one single epsilon, then you can just scale the B and W and it will work for any epsilon. So there's various ways to think about this, but basically that allows us to essentially say, all right, let's just focus on epsilon equals 1, the simplest thing. So the question now is, or the statement of linear separability says, there exists some B and W such that this holds for all I. So in other words, the sign corrected score is greater or equal to 1 for all the samples in that data set. So that's what we have now for linear separability. And then the very last step was we used this equation to replace this score here with the distance to the boundary. So here we have the sign corrected signed distance should be greater than some fixed number, 1 over the norm of W, for all the samples in the data set. Okay, so that's what it means to have a linearly separable data set. And moreover, it tells us that this quantity, which we call the margin, is going to be a lower bound on all the distances from points to the boundary. So like in this picture here, we have all these training points here. This is a linearly separable data set. And you can see that all these points are, at least this gamma, this distance gamma from the boundary. So this gamma, or the margin, is a lower bound on the closest one, the minimum distance. The points closest to the boundary are the most difficult points. They're the ones hardest to classify. So this tells us something about the difficulty of this data set. Or let's say the difficulty, or maybe we could say the robustness of the classifier. So what we reasoned last time is that this classifier is quite robust because we have oriented the boundary to have quite a large minimum distance. On the other hand, if we would have chosen the classifier this way, even though that still perfectly classifies the data, now the minimum distance is much smaller. And so that would be a less robust classifier. And in fact, the training, even though this is the training data, looks like this, maybe the test data would put a circle point over here, and then it would make an error. So that's what we don't want to happen. And so we want to try to make our classifier as robust as possible, essentially by maximizing the margin, maximizing the minimum distance of all training points to the boundary. And that's kind of what we're doing in this unit in a nutshell, is we're looking for these maximally robust linear classifiers. Okay, any questions about anything I've said so far? So some of these ideas are a little bit tricky. You got to kind of think through them. Okay, so now we basically have all the pieces, all the ingredients we need to actually design a classifier. So the key point here, the key equation is this margin. So you can see that if my goal is to maximize the margin, gamma, then equivalently I can minimize the norm of W, right? While keeping the data linearly separable. Because if we didn't have the linear separability constraint, you could just get a bad classifier and you can make the norm of W 0 if you want. That's not really, this has no meaning unless this linearly separable thing is happening, unless the classifier is separating the data. So we really want two things. We want, number one, a classifier separating the data. Number two, for that classifier, we want that this margin is maximized. Okay, is that kind of clear? So with that, this is how we can do it. We'll call it the hard margin classifier. And this is the math problem, the optimization problem. Minimize. Okay, the 1/2, you can see that that's just there for nice derivations. And the squaring here is also there to make the derivation easier. But you can essentially see this term is trying to minimize the norm of W, right? Because we said minimizing the norm of W is maximizing the margin. That's what we want to do. But then this part, this is a constraint, such that this inequality holds for all data points. This point is ensuring that we have linearly, that we have linear separability. Because without this, minimizing the norm of W is not useful. Okay, so we have those two pieces together, and this is the hard margin classifier. We have some optimization problem. As you can see, we're minimizing a convex loss in W subject to an inequality constraint, or actually n different inequality constraints. So this is stuff we talked about at the end of Unit 6. We talked about convex optimization. We talked about constrained optimization, equality constrained, inequality constrained. So here we're kind of seeing it come to fruition. So basically, this is a problem that can be solved by some methods. We talked a little bit about dealing with these inequality constraints. We said it's a little complicated. It involves these KKT conditions. We didn't get into the details. It's not important. The main important thing right now is just to understand the overall construction, like why is this term here? Why do we have these constraints? So any questions on that part? Yes?
I understand that the half over there shouldn't make any effect on minimization, but why is it there?
Why is the half there? Is because when you take like a derivative of this, the 2 cancels the 1/2 and it looks prettier. If you don't have it there, then you have 2's all over the place. Yeah. Yeah, and then the squared is there too, because with the squared, the norm squared is the sum of squares, but otherwise there's a square root, and the square root is also kind of messy. So that's why those 2 things are there. Okay. Great. So everybody is good on why we're doing this and why we're doing this? Okay. So if you want to maybe understand this in words, I think this sentence tries to do that. So it basically says, like, of all the BW pairs that satisfy our linear separability constraint, the one yielding the widest street, this is like the width of the street, the one yielding the widest street is going to be the one with the smallest norm of W, or norm of W squared. So it's kind of like saying, consider all the different ways I can make a classifier that does separate the data. As you move that around, if you measure the width of the street, you will find that at this sort of magic position, which is illustrated here, that is the one where you will get the smallest norm of W. And that is kind of understood by here. We proved that this 1 over norm of W is that minimum distance. Okay, so that's trying to explain the idea in words. Okay, so any questions on this? I know these are not the easiest of ideas, so does anybody have, like, if one person has a question, probably other people have the same question, so don't be afraid to ask. Okay. All right, so just visually speaking, when you do this, what's going to happen is that you're going to have a few points that are right on the boundary, right? At least, well, I guess there's some cases where you can do it with 2 points, but in most cases there's going to be 3 or more points that are going to be used to determine exactly where it's right. Just kind of visually, if you imagine moving that line around to maximize the width of the street, at the end of the day, you're gonna use like these 3 points, and you're gonna ignore all the other points. All the other data samples are ignored. So this whole design basically hinges on these 3 samples. So this is accomplishing that task that we saw earlier in the unit when MLR was somehow it was designing the W vectors that seemed to make more sense when there was a few samples, and then as there was more and more samples, it seemed to do something like overfitting. So here what we're saying is we have built a method that is all about figuring out which samples are the hardest to classify and using exactly those samples and not getting distracted by any of the easy samples to classify, which are these. So that's what we've done. Okay. So that's all good, but there's one big shortcoming of this version of the method, is that this only works, this hard margin classifier idea. It requires the data to be linearly separable. Because if we have a data set that is not linearly separable, that means there is no B&W that can achieve this, and then therefore we can't solve this problem. Right? Because we said that's a requirement for the way that we're setting things up. So this is just the first step along a way of understanding how to solve general problems. So this certainly works if you're given a linearly separable data set, but it doesn't work more generally. So the next step is to modify this idea so that it will still work even if the data is not linearly separable. And we're looking for something that works the same as this, but just extends the coverage to more general cases. So in order to do that, the main idea is we're going to replace the hard constraint, which we saw previously. So here is our hard constraint. We're going to replace this with another loss term that we're going to add to this. So let's see how we can do this. So here's the hard constraint written exactly as we had on the previous page. So you can see that I can subtract the left side from both sides of the inequality, and I can rewrite this hard constraint this way. So this is going to help us understand the cost term that we're going to add. So the cost term we're going to add is this. So this is the max of these two values. So whichever one of the two values here is larger, the max is going to choose that value and report that value. Okay, so let's think of the two cases. So in the case that the data is linearly separable, that means that this inequality holds, right? It also means this inequality holds. And in that case, it means that this quantity is less than or equal to 0. So in that case, when I take the max of 0 and this guy, we said that this guy is less than or equal to 0, so the max will return 0, right? So in other words, whenever the data is linearly separable, this whole cost will equal 0. Or this term will equal 0. And this is something we want to minimize. So basically, in that case, we've driven it down to the lowest possible value. We're happy. Now, if some of these data points fail this inequality, for that ith data point, this number will fail. So this number will actually be strictly greater than 0. And in that case, you can see the max of 0 in that number will return that number. So what happens then is this cost starts increasing. So the more points I that are violating this linearly separable constraint, the larger this cost gets. So when you optimize, so this is the new optimization problem. This part is from before, and now we're adding this new thing multiplied by some weighting term C. So we'll talk about the effect of C in just a moment. But you can see that when you do this minimization, you're simultaneously trying to make sure that there's no violations of your linear separability, right? So in some cases, you can squash this part all the way down to 0, which means there's no violations at all. But you're also trying to minimize this. And so minimizing W, if you remember, that is the same as maximizing the margin. So you're like simultaneously saying, I want the street to be as wide as possible, and I don't want any samples in the street or on the wrong side of the street. I want all the samples to be outside the street on the correct side. That's sort of what you're doing simultaneously here. But there's sort of a tension between those things because as the street gets wider and wider and wider, there's no way to prevent samples from being inside that street, right? So these two things are sort of fighting against each other. And so you need some way to balance them. So that's what this parameter C is. It's some tunable weight, C, something we have to choose. And that is actually going to do some sort of trade-off between what I would call the number of margin violations. So every time this is not true, that adds to this. That's like a violation in the margin. It's trade-off between that and this margin size, gamma. It's trading off between those two things. So let's imagine what happens when C is really large. If I make C really large, that is essentially saying I really care about this a lot more than this. So when I minimize this, it's almost like saying I only care about this and I don't really care about that much at all. So in that case, what you're going to do is you're going to try to find a street such that you make as few violations as possible. So that's going to be a narrow street, right? Now, if your data is not linearly separable, no matter how narrow the street is, if the street collapses to a line, there's no way to prevent margin violations because you have samples on the wrong side of the line. So that's impossible. So you're definitely going to have some cost, but that's inescapable. So that's what happens when C is large. You try not to penalize the margin, and you try not to penalize these, and you allow a really small street. On the other hand, as you make C small, it says, okay, I don't care as much about violating the margin, and I will allow this 1 over norm W to be very large. So my street now is going to be really wide, and it's okay if samples are in the street on the wrong side because I don't care about that as much. I'm more interested in just making the street really wide. So those are the trade-offs you have. So here's saying the same thing again with some pictures. So again, larger C means that the margin gets smaller, the street gets narrower, and that would be an example here. C is 1,000. In this case, the circled ones are the support vectors. Those are the ones used. So you can basically figure out where the street is just by looking at these circled points. So the street is somewhere. Sorry, it's not a great drawing, but something like that. It's very narrow. On the other hand, now if we decrease C from 1,000 to 10, you can see that now the street has gotten wider. And if we decrease C from 10 to 0.1, now the street is super wide. So because in this case, when we set up that optimization problem, we said what's most important is not violating that margin constraint. So we don't want any samples in the street or on the wrong side of the street. And for this data set, it's hard to tell visually whether it's linearly separable or not, but it very well might be. As C decreases, we say we don't care about violating that margin constraint. So now we have some samples that are in the street. And in fact, we even have some samples that are on the wrong side of the street, which did not seem to be happening over here. It doesn't look like we're making decision errors with that classifier, but with this classifier, we are making decision errors on the training data. And if we go further, now we're saying we want the street to be super wide, and what happens is we make even more decision errors. So these guys, at least one of them was previously correct and now it's incorrect. So a nice way to think about this is through the bias variance trade-off. So as we know back from unit 4, the more training samples you use, your variance decreases, right? So in this case, when we have, okay, so let's talk about bias first. It's a little bit easier. So bias basically says what's going to happen, what's sort of the average case performance. So imagine that you do this experiment over and over again, where somehow you're randomly generating these points according to the same statistical model. So every time you do this experiment, where those points end up is slightly different, but let's say something like the true generating model is the same. So when you imagine that happening, on average, you're going to be doing pretty well here. You're not going to be making too many errors when you look at what happens on average. But notice that what happens on every given experiment, you're only using something like 8 samples here. So as those 8 samples are varying, the exact location of your boundary is going to be jittering around quite a bit. So that causes variance, right? We know changes across experiments, that's variance. And we know that the fewer training samples you have, essentially we're only using like 8, we're throwing away the rest. The fewer we have, the larger the variance. So here we see an example of low bias, high variance. Now, as we decrease C, we're using more and more of our training samples to determine the boundary. And so what that means is across experiments, you will see less variation because this boundary is the average in some sense of those samples. The more samples I use, the less variation I see. So this boundary will be quite stable across experiments. It won't really move much. This one will move much more. So the variance will be lower here. But as you can see, the average case performance is a lot worse. We're making a lot more errors here than here. So the bias here will be high bias, low variance. So the bias variance trade-off gives us a way of understanding the effect of this penalty weight in our support vector classifier. Okay, does that sort of make sense? Any questions on anything here? Okay, another small comment is, so generally speaking, as you increase C, you see that there's fewer and fewer support vectors. The support vectors are the ones that we use to determine the boundary. So there's fewer and fewer, but at some point, you're gonna find the minimum amount of support vectors possible, and even if you increase C larger and larger, nothing will change. Like maybe this, like in this picture, the minimum number of samples you need to determine this boundary is 3. So no matter how large C gets, you're always going to be using those 3 samples, and your street will always be this width. It will not keep shrinking. So generally speaking, as you increase C, you tend to see fewer and fewer support vectors until you reach the minimum. And at that point, things don't change. Your classifier design doesn't change. Yeah.
In the minimization function which you had in previous slide, from what I understand, C is independent of N. N is basically the number of samples which we are using. So when you are actually doing the classification, how is N affected by C?
Well, I mean, N is something that is fixed for a given data set. Right? N is just the number of samples in the data set. So I don't know if you're asking this question, like if I have a very small data set and a very large data set, could I use that to guess an initial C? Is that what you're asking? Or?
Not exactly. My question is basically how high are the number of support vectors you're using on XPC?
I mean, so the number of support vectors really just depends very much on how much overlap there are between the classes. So, if you have a lot of overlap between the classes such that the very best linear classifier still is going to make errors, then you're going to have, it's impossible to avoid a large number here. On the other hand, if you have linearly separable data, as you increase C, eventually you will come to the point where you are perfectly separating your data, and the value of this will be 0. So really depends on the data set how big or small this can be, and then that sort of affects this weight. The weight C is basically trading off between these two terms.
So when you say that, you're basically saying that you are changing N when you are changing C, right?
No, I mean, N is a fixed number. N is like just the number of samples in our data set. So we can never change that. For a given data set, that's just fixed. The number of support vectors, are you wondering about that?
Yes.
So the number of support vectors are the number of points for which this is 0 or less. Sorry, 0 or more. So if this is strictly less than 0, it turns out that sample will not be used at all. If this is exactly equal to 0, then the sample is right on the boundary of the street. And if this is greater than 0, then it's either in or on the wrong side of the street. Yeah, number of support vectors is basically the number of violations or like, maybe not violation, but right when you're on the edge of the street. So in this case, this picture, we had 3 support vectors. But if I had a black dot over here, then there's no way to, that would be another support vector, and there's no way to escape that. Okay. Yeah, there's a lot of things to understand in here, so I don't mind talking about it and answering some more questions, because it's on one hand the math looks very opaque, but there's real ideas in here that I don't think are quite as challenging as maybe the math looks. Okay, does anybody have any other questions? Yeah.
So just with the slide with the 3 pictures that are all the support vectors circled.
Oh, yeah.
So it looks like all the support vectors are like on the inside of the street, since they're, or are they supposed to be on the borders? Or the one with the lowest C.
Okay, so this one, so for this one, there's going to be, I don't know exactly where the street is, but probably there's going to be some here that are right on the edge, or at least one of them will be on the edge. And then all these other ones we would say are inside the street. A few of them are inside and on the wrong side of the street. So all of these points that are circled will be the ones for which this is 0 or greater, and they will contribute to increasing that part of the cost. Meanwhile, the smaller, so in that case, because this is relatively small, when you do this optimization, it's focusing on making this very small. And as the norm of W gets small, that means the street gets wide. So that wide street is because this optimization really focused on making this small, which made the street wide, and it said, oh, I don't care if there's a lot of violations. That's not what's important to me, because what's important is, the combination of these. And if this is really small, then this is not as important as this. So that's why it says, let's use a really wide street, accept all those violations. That's fine. That's what you asked for. Okay, good. Is this making a little more sense? Okay, are there any other questions? Okay. All right, so one thing that is super insightful is to compare this to logistic regression. So if you remember logistic regression, the binary cross entropy cost is like this part. We derived this back in Unit 5. But then we said that when you implement it in practice, like in scikit-learn, by default, you tend to add this L2 regularization, because if you don't, and you happen to be working with a linearly separable data set, minimizing this alone will actually cause your B and your W to go off to infinity. You don't want that. So to prevent that from happening, you just put maybe a small term here. So you would use a very large C, very small weight on this, and that would just prevent the parameters from going to infinity. So this is what we derived before. And so this SVC, okay, so this SVC here, so we said it's like this, right? But we could just equivalently divide both terms by C, and that puts the C down here, and that's essentially the same optimization problem. So now when you compare that's this. When you compare that to this L2 regularized logistic regression, they look almost identical. The only difference is the function of y and z here. So to gain some insight in that, we can actually plot that function. And so at least one way to view this plot is plot it for yi equals 1. That's maybe one way to think about it. In that case, the logistic loss gives you this curve, whereas this thing in the SVC, which is known as the hinge loss, that gives you this curve. Okay, so they're very similar. One of them, logistic loss, is a nice smooth curve. The hinge loss is this sharp curve. It's nice in that it's linear. It's basically, there's a linear segment here, there's a linear segment here, so it's very elegant and simple. And here you can see this value 1. This is essentially when yz is equal to 1, that's right when you're at the point where the max, is, where the two things you're maximizing is equal. So once yizi gets greater than 1, then the max just chooses 0, and that's what happens. So that's where you get this flat part. And then on the other side, you essentially have something that's linear with slope -1. Okay, so this gives us intuition because it clarifies what is the difference between what we were doing before and what we're doing now. We essentially just changed this nice smooth curve to this simpler linear one. And the key interpretation of it is what's happening here. So we know that essentially this hinge loss places no penalty on any samples for which this yizi is greater than 1. So right, for any samples which are over there, the hinge loss says, I don't care. I'm not going to use that in my design at all. For logistic loss, though, it still uses them. It uses them maybe not very much. It weights them a little bit, but it does still use them. And so this is sort of the difference. SVC uses only these support vectors, which are the samples xi, for which this is less than or equal to 1, whereas logistic loss uses all samples to come up with its design. And that's what we saw before when we were looking at the MNIST examples. We saw that as the number of samples we used to train logistic regression grew large, it seemed to be doing some weird stuff. And perhaps here again you can see maybe what's happening is it's getting distracted by these easy to classify samples. It's still using them instead of the support vector classifier, which is only going to use the ones that are harder to classify, the hard samples, hard training samples. Okay, so there's all these different ways to understand this SVC. Okay, so, all right, so is this pretty clear? Any questions on this interpretation? Good? Okay. So to try to help some of what we're going to do later, we can look at the support vector classifier in a different way. So this is, again, this is the cost we're trying to minimize. And so you might say, a little bit naively, you might say, well, what we often do with a cost function is we try to take the derivatives with respect to the parameters, in this case b and w, and we try to find the values of b and w that set those derivatives or gradients to 0, right? That's been our approach all along. So we can try that here too. So the first thing we can try to do is, let's take the derivative of this with respect to b and set that to 0. Okay, so it's a little bit complicated by this max function. So let's consider some different scenarios. So, so let's say first, what if this term here is strictly less than 1? Okay, if this is strictly less than 1, then 1 minus that is strictly greater than 0, which means the max will always choose this. At which point we can forget about the max altogether, and in this case, essentially we just have a sum of these values. So in that case, we can do the gradient pretty easily, right? So we take the gradient of this with respect to b, or the derivative with respect to b, and you can see that's just going to be minus yi for each of these. So I'm writing that this way, and I'm using this variable ai, or alpha I. So now alpha I will be 1 for this case. Okay, so for this case, we just get this expression for this. Is that pretty clear? Okay. Now let's consider another case, which is where this is strictly greater than 1. In that case, 1 minus that will be strictly less than 0. And the max will always choose 0 no matter what. So in that case, when you take the derivative of this with respect to b, because it's just 0, the derivative is 0. So we can write the same expression, but now using the alpha I as 0. Okay, so that when all the alpha i's are 0, this whole thing goes to 0. So we now have kind of a common expression that works in both of these cases. The challenging part comes when you look at these values that are exactly equal to 1. So in that case, when these are exactly equal to 1, the result is 0, but what's actually happening is that if you look at what happens as b is shrinking towards this, or if b is growing from below, you actually have different slopes. And so it's like you have a situation, we have a function like this, and as from in this function, when I look at the gradient or the slope here, the slope is always 0. When I look at the slope here, the slope is always minus 1. But right at that point, the slopes do not agree from either side. And that is a point of non-differentiability. So that is exactly what happens here, is that when you look at this value where this exactly equals 1, and you consider what happens coming from either side, there's a clash, and there really is no gradient. So to handle that, I'm just going to write question mark, because gradients are just not the real framework to handle this. There's a more complicated framework involving something called subgradients, but we're not going to get into that. So we're just going to put a question mark here, and this is all just to try to get some intuition into this problem. Okay, so this is our gradient or derivative with respect to b. We get this expression, where at least in most cases we know how to interpret it, but there's this weird middle case that happens, for it only happens for the samples that are exactly on the edge of the street. For those samples, we're not sure what's happening. Okay, now we can do the same thing with the gradient with respect to w. And in fact, the math is the same. We first consider this case, in which case we can get rid of the max, and then we take the gradient of this with respect to w, and you get minus yi times xi. And so we write this, again, with alpha I equals 1. And then we do it for the other case, where we have only the 0, take the gradient of 0 with respect to w, and you get 0, and we handle that by putting the zeros in for these alpha i's. Oh, and there's this one other term. The gradient of this with respect to w is always going to be w itself. Okay, so we now have derivative with respect to b, gradient with respect to w, and you can see from these two equations now we can solve for a couple things. So from the first one, we can see that what we will need is we will need that this happens. So this is a property of these alphas, that they must, alpha I times yi must sum up to 0. Okay, that's still not enough to figure out what's happening with all those alphas, but you get a little bit of an intuition about that. Yes, there are some particular values they need to take on for this to hold. And second, from this part, you can just say w equals this. So these are this with the star. That's the optimal w, the optimal b. I probably should have written hats, because hats are how we've done that with previous slides. So you can think about these as hats if you want, but they're just the optimal parameters. Okay, so regardless, what we see from these expressions is that you can see exactly how the optimal weights are constructed from the training samples. And in particular, you can see that for certain training samples, the ones which you get the 0 alpha, those are the ones where those training samples do not affect w at all. So here's another way to see the support vector idea, that yes, w is only going to be determined by the xi and yi for which this holds, because that's, or actually both of these cases, because otherwise you get zeros here, and those xi, yi don't affect w. So let me just highlight these two equations. These equations, we will see these come back again. So that's part of why we're doing this. And then the other part is, even though we have the question mark here, we still can say that these support vectors are going to be the xi's for which this is less than or equal to 1. Okay, so any questions on this page? Okay. Let's also think about what happens when we apply this SVC to test data. So until now, we've focused on training it. So now let's say we've trained it, so we know what these parameters are. So we said essentially, if x is a test vector, we'll make a test score with this equation, which holds for any linear classifier. But now for the SVC, we have this particular expression for the optimal weights. And we also remember that these alpha i's are 0 for all x that are not support vectors. So if I just plug this in for my w expression, then I get this expression for the score. And you can see a little bit about how the score is constructed. Essentially what's happening is that you're taking your test features and you're doing these inner products with all your support vectors. It's like you're doing some kind of comparison of the support vectors and your test vector, and then you're combining those according to the labels yi and these numbers alpha I. So it gives you a little bit a sense of what's actually happening when you're doing the classification. So it's a linear combination of the inner products between xi and each support vector. So SVC is trying to focus on what's important when making a decision rather than just using all the training samples like logistic regression does. Okay. So, all right. Any questions on this. All right. Okay, so if you go to the Wikipedia page for the support vector classifier, you'll see things written in a slightly different way that might look a little bit unfamiliar, and I just want to show you that it's actually very similar, just a slight deviation in how things are expressed. So what they do on the Wikipedia page and many other sources is that they essentially, so this is, and this is what we've been focusing on. They essentially replace this with a number they call, or they write as xi. So they just replace this with xi. They're called slack variables. Okay, so this is exactly our SVC loss written in terms of the slack variables. Of course, now that you've made that substitution, you have to somehow describe this constraint on the slack variables. And you can do that as follows. So according to how these are constructed, you can see that this must be greater than both this and this, right? Because it's the max of the two, it must be greater than both. So you can now write that as xi is greater than or equal to 0, and xi is greater than or equal to this. And that has to happen for every I. Okay, so this is just a different way of writing the same thing that we wrote. It's, we wrote it as an unconstrained optimization problem. Now you have another problem that is actually a constrained optimization problem. You have these two inequality constraints for each I and this cost. But it's the same. It's just a different way of writing it. Okay. There is an interpretation, though, of these slack variables. They essentially are measuring how much the margin is violated. So if the slack variable is 0, that means there is no violation. It basically means that the sample is either outside the street or right on the edge of the street. So, for example, if we're talking about these blue samples here, all of these guys would have a slack variable of 0, but this would have a slack variable equal to this distance from here to here. Remember that the distance from, I guess this is a normalized distance, so as you go from here to here, that would be like, okay, if you're on the boundary, that means z is 0, and you can see then that the slack variable would be 1. So as you go from here, slack variable 0, here slack variable is 1, here slack variable is 2, here slack variable is 3. The further you get on the wrong side of the boundary, the larger that slack variable becomes. So just directly measuring how much you violated things. So all these, no violation, 0, but then anything here or there, non-zero. So then, okay, if the slack variable is between 0 and 2, but not, either 0 or 2, that means you're strictly inside the street. And if the slack variable is greater than 1, that means you're actually on the wrong side of the decision boundary. You will make a mistake. So like this red one is actually on the wrong side. It's on the blue side. And this would have a slack variable about, roughly 1.5. So it would be misclassified. And so there's a bit of an interpretation to these, but it's mainly, I'm just telling you this in case you see this in another source that you understand it's really the same thing. Okay. I think that's a good place to stop. We'll talk more about multi-class, SVC, scikit-learn implementations, but what we did today is probably the hardest stuff. So the following lectures should be a little bit more easy and intuitive. All right, so we have a fall break on Friday, so I hope you guys have a great weekend, and we'll resume this discussion on Monday. See you then. Oh, and if you haven't picked up your midterm, please pick it up for me. Otherwise, I think you're absent.